Chapter 14, Temperature and Heat Transfer. This lecture will help you understand heat transfer. Heat can be converted to useful work. In our bodies, when food is oxidized, heat energy is produced, which can be converted into muscular energy, which in turn can be turned into work. When a gas is burned, the gas expands and builds up a tremendous pressure that may convert heat to work by exerting a force to move a piston in an engine or turn the blade of a turbine. Heat from burning oil, coal, or wood may be used to generate steam. When water changes steam under atmospheric pressure, it expands about 1,700 times. When confined to a boiler, the pressure exerts a force against the piston in a steam engine or against the blades of a steam turbine. The process of thermal energy or heat transfer are conduction, convection, and radiation. Conduction is the transfer of internal energy by electron and molecular collisions within a substance. Conduction is the heat transfer from a warmer part of a substance to a cooler part as a result of molecular collisions, which cause the slower moving molecules to move faster. Conduction is the usual method of heat transfer in solids. When one end of a metal rod is heated, the molecules in that end move faster than before. These molecules collide with other molecules and cause them to move faster also. In this way, the heat is transferred from one end of the metal to the other. When you stick a nail into ice, does the cold flow from your ice to your hand or heat from your hand to the ice? Cold does not flow from the ice to your hand. Heat flows from your hand to the ice. The metal is cold to your touch because you are transferring heat to the metal. Insulation doesn't prevent the flow of internal energy. It merely slows the rate at which internal energy flows. Rock wool or fiberglass between walls slow the transfer of internal energy from a warm house to a cool exterior in winter, and the reverse in summer. Snow patterns on the roof of a house shows areas of conduction and insulation. Bare parts show where heat from inside has conducted through the roof and have melted the snow. Good heat conductors are composed of atoms with loose outer electrons. Good heat conductors are poor insulators. All metals are good conductors to a varying degree. Copper, aluminum, and steel are good conductors. Poor heat conductors delay the transfer of heat and are good insulators. Examples are wood, wool, straw, paper, styrofoam, asbestos, glass, snow, fiberglass, cellulose, cork, liquids, gases, air, and materials with trapped air are poor heat conductors. As a dramatic example, you can walk barefoot without burning your feet on red-hot coals due to the poor conduction between the coals and your feet. Heat conduction is quantified by thermal conductivity. The thermal conductivity of several materials is given in the table. The units of thermal conductivity are either joule per second per meter per degree Celsius or BTU per foot per hour per degree Fahrenheit. The total amount of heat transferred by conduction is defined as Q equals K times A times T times T2 minus T1 divided by L, where Q is the amount of heat transferred in either joules or BTU. K is the thermal conductivity from table 14.2. A is the cross-sectional area of the material. T is the total time of contact between the two materials. T sub 2 is the temperature of the hot side. T sub 1 is the temperature of the cool side. And L is the thickness of the material. Find the heat flow in an 8-hour period through a 36-inch by 36-inch pane of glass, which is 0.125 inches thick. The temperature of the inner surface of the glass is 65 degrees Fahrenheit, and the temperature of the outer surface is 15 degrees Fahrenheit. The data are the thermal conductivity of glass are 0.5 BTU per foot degree Fahrenheit hour. The cross-sectional area is 9 square feet. The total time period is 8 hours. The hot side is 65 degrees Fahrenheit. The cold side is 15 degrees Fahrenheit. And the length or thickness is 0.0104 feet. The working equation is Q equal KAT T2 minus T1 over L. Substituting the numbers we know, the total heat flow is 1.7 times 10 to the 5 BTU. The R value of insulation is defined to be the length of the material in feet divided by the thermal conductivity, where R is the R value in feet squared, degree Fahrenheit, divided by BTU, divided by hours. K is the thermal conductivity, given in table 14.2, and L is the thickness or length of the material in feet. Calculate the R value of 18 inches of cellulose fiber insulation. Our data are the thermal conductivity of cellulose and the length or thickness of the insulation. The working equation is the definition of R value. Substituting the numbers, we get a solution of 65 feet squared, degree Fahrenheit, BTU per hour, which we normally just say 65. We leave off the units when talking about R values. Convection is the transfer of heat involving only bulk motion of fluids. Examples are the visible shimmering of air above a hot stove or above asphalt on a hot day. Visible shimmers in water are due to temperature differences. Cooling by expansion is the opposite to the warming that occurs when air is compressed. An example, the cloudy region above hot steam issuing from the nozzle of a pressure cooker is cool to the touch, a combination of air expansion and mixing with cooler surrounding air. Careful, the part of the nozzle that you can't see is steam, which causes severe burns. Convection currents in air are produced by unequal heating of land and water. During the day, warm air above the land rises, and cooler air over the water moves in to replace it. At night, the direction of airflow is reversed. You almost always experience a breeze at the ocean shore. Convection is the reason warm air rises. Warm air expands, becomes less dense, and is buoyed upward. Air rises until its density equals that of the surrounding air. Smoke from a campfire rises and blends with the surrounding cool air. Although warm air rises, why are mountaintops cold and snow-covered, while the valleys below are relatively warm and green? A, warm air cools when rising. B, there's a thick insulating blanket of air above valleys. C, both of these. D, none of the above. Answer is C, both of the above. Earth's atmosphere acts as a blanket, which for one important thing keeps Earth from freezing at nighttime, and warm air cools when rising. Radiation is the transfer of energy via electromagnetic waves that can travel through empty space. Radio waves, infrared waves, and visible light are all forms of electromagnetic radiation. The wavelength of radiation is related to the frequency of vibration. Low frequency vibration means long wavelengths. high-frequency vibration mean short wavelengths. Every object above absolute zero radiates. From the sun's surface comes light, or solar radiation. From the Earth's surface is terrestrial radiation in the form of infrared waves below our threshold of sight. Even people, plants, and animals radiate, but very weakly. A low temperature or cool source emits primarily low frequency, long wavelength waves. A medium temperature source emits primarily medium frequency waves. And a high frequency source emits primarily high frequency or short wavelength waves. A thermal infrared camera shows hot spots in brighter colors. From cars to people to animal to houses to galaxies, all objects emit some infrared radiation, just in different amounts.